Well, thanks, Emanuele. That was a friendly, very, very appreciated introduction. I would like to start with an anecdote as well. So the last time I was from this side of this specific room was during my master thesis discussion. And there was this anonymous, let's say anonymous member of the committee who asked me a super difficult philosophical question about the Dirichlet process. And to this day, I still don't know the answer to that question. So please be kind, because there is the Dirichlet process even in this presentation. So let's see how it goes. So, well, jokes apart, I'm super happy to be here. This is a work that starts as grounding some Bayesian parametrics, but then moves towards something related to exponential families, which is a great, and so this, I think it's a great place to talk about that. And instead of starting with just a lot of formulas, I would like to start with, well, first of all, some warm thanks to the co-authors. So this is a joint work with Chin-Lung Su, Alessandro Zitto and David Danson. So they were all at Duke University when we started doing this work. Now they moved a bit, but that's a joint work with them. So this is a combination of two works, the first one with Chin-Lung, the second one with Ale Zitto. And so, as I said, instead of starting with formulas, I would like to start with a little bit of a story. And my apologies if some of you may already heard about it or listened to that story before, but let's start with this. So with this biodiversity timeline. So as the title of the talk suggests, I'm going to talk about biodiversity, its estimation in Bayesian inference. And of course, I'm not the first one to cover this topic. And so probably the first paper on that is this incredible paper by Ronald Fisher that was mentioned yesterday during the talk of Andrea Tancredi. Was in a footnote, I think, but that's the paper. So Fisher introduced this model, those ideas. So essentially, in biodiversity, when you collect species, what you get as a data are the abundances, so the frequencies of those species, and you can record whether those are singletons, doubletons, and so on and so forth. So how many times you observe a given species. And the abundance, the expected number of species appearing R times under Fisher model, is governed by that formula there. So there is a constant, a proportionality constant, alpha, which is going to be like our super important parameter. And then you have this power series, which is decreasing over R. X is another constant that you estimate from the data, but that's Fisher model. And so Fisher proposed, after a lot of calculations, to estimate this alpha constant as a solution of this equation, which doesn't have a closed form, but it's very simple. So essentially here, the two key ingredients are the number of distinct species that you have in a sample and the total number of the sample size. Okay, so you have, let's say, 100 recorded individuals, and 10 of them or 15 of them are distinct. You solve this equation and you get the alpha number. So that was Fisher's idea. Then we have other classical proposal, other classical approaches, the one by Good and Tulming related to the sample coverage, the estimation of the number of species. I'm not going to cover that in the details of that, but they're also related to this topic. And then after, in 1972, there is this paper in genetics by Ewens. And so now you can start to see that the alpha is appearing once again. So this is not by chance, it's not going to be a coincidence. So this formula here, indeed, was applied to genetics. So now M1 represents the singletons, M2 represents the doubletons, and so forth. So this is a distribution of the singletons, the doubletons, and so on and so forth. And it's very famous that this distribution here is related to a well-known quantity in Bayesian parametrics, which is the Dirichlet process. Okay, so this is a one-to-one correspondence with a paper by Ferguson, Thomas Ferguson, and Antoniak, actually. So the law of the partition, so to fix ideas, M1, M2 are the singletons, doubletons, and so on and so forth. Instead, N1, N2, and 3 are the abundances. So how many times I actually observe a given species. And once again, there is this alpha parameter, which is known as the precision or concentration parameter of the Dirichlet process. And as is well known, the Dirichlet process admits a sequential construction. So you pretend essentially to observe species one at a time. So you start, well, the first species is new, always, it's a new species. The second one there is a given chance to get a new species, and this is new with probability alpha over alpha plus n. So at the second step is going to be alpha plus 2, and you proceed in this way, okay? Alpha plus 1 actually. And so this is the Blackwell and McQueen-Ern scheme, characterizes the partition. So there is a lot of theory going on over there. Then, after the Dirichlet process, we had Pitman model. So Pitman essentially generalized the Dirichlet process to a broad class called species sampling models. I'm not going to cover the whole topic here, but the important bit is that it introduced a notion called sigma diversity. So sigma diversity is nothing but a rescaled, standardized, if you want, richness. So the richness in ecological terms is nothing but the number of species that you get in sample. You divide that by a deterministic function, which in the Dirichlet process is going to be the logarithm. And the richness divided by the logarithm converges to something, which might be either a constant or a random variable, depending a bit on the context. In the Dirichlet process case, this is a constant, and is once again alpha. Okay, so then what? Then this guy, appear in the timeline. So Hubble is not a statistician. He is a physicist, mathematician. He worked a lot in ecology, and he wrote this book called The Unified Neutral Theory of Biodiversity and Biogeography. So this is a long book, and it describes this unified theory of biodiversity and identifies alpha as twice the meta-community size times the speciation rate. So it turns out that this alpha is nothing but the very same thing of the precision parameter of the Dirichlet process, which is nothing but the original alpha parameter of Fisher. So everything is interconnected. So basically, all those people were talking about the same model. So Ewens was aware of the work of Ewens, but probably not of all the other papers in Bayesian and parametrics. So we close this story with this discussion by Peter McCulloch. So this is the discussion of a statistical science paper about the Dirichlet process. And so in McCulloch's words, we say that it's fair to say that Fisher almost discovered the Ewens sampling formula. He had it in his grasp. After all, he had only to compute the conditional distribution given the sample size, a task that was both statistically natural and for him mathematically trivial. Actually, if you go through the details, what happens is that Fisher models is nothing but the marginal likelihood of the Ewens sampling formula. So the conditional likelihood of Fisher model is the Ewens sampling formula. So the two things are actually very strongly interconnected. And there is even an even stronger relationship once you compare Fisher estimator with the maximum likelihood estimator. So they truly are connected. So this is very heuristic. So since I have a bit of time, let's go through the mathematical details a little bit, so to get a better sense of all these ideas. So this is in modern terms what we would say. So a species sampling model is nothing but, okay, so the notation here is very is technical and specific of the Bayesian and parametric community, but it's nothing but it's essentially a multinomial model. Okay, so we have the data points xn that are sample IID, conditionally a random probability measure, and this random probability measure is discrete, and pi h are the proportions of the species. Okay, and so because the distribution is discrete, you will have ties, so certain species will be reobserved with certain frequencies, and y is the number of distinct values that you get in a sample. A natural generalization of the Dirichlet process is the class of Gibbs-type priors. So here I'm presenting you a general class of priors. So essentially, you put a prior on those random weights pi h and the random variables zh. You marginalize them out, and what you get is a sequential mechanism. This is essentially the predictive version of in the style of Sonia's talk this morning. Okay, so this is truly predictive, originated from a Gibbs-type prior. So essentially, what you get is this quantity here, which is the probability of observing a new species, and those quantities here that are essentially proportional to the frequencies that govern the probability of reobserving something old. Okay? So the VNK must satisfy some recursive equation, but it's something we leave there. Also, it's important to know that there is a parameter, sigma. When sigma is equal to 0, an example is the Dirichlet process. When sigma is positive, between 0 and 1, you get, for example, the Pitt-Maillard. When sigma is negative, you get the Dirichlet multinomial. Okay. So those are 3 examples. So the first 2 examples are very simple, very natural. The third one is ugly, but there is a reason why I'm presenting you that. So the first one is the Dirichlet multinomial. The Dirichlet multinomial means that you put a Dirichlet priors with the h components to the weights, so it's finite dimensional, and that's it. So you marginalize them out, and that's the formula you get. Okay, so this is just that's why you get that formula. In sigma equal to 0, you have, as a representative, you have the Dirichlet process. So the VNK here is drastically simple, okay? And once you plug in those weights into the previous formula, you get the Blackwell and McQueen recursive formula. This one is the ugly one. So it's the sigma stable Poisson-Kingman process, okay? With sigma between 0 and 1. And so you may argue, especially those familiar with that, why don't you present the Pitt-Maillard, which is much simpler? There is a reason why. So those 3 examples are not just 3 examples. So those 3 models are the building block of any Gibbs-type priors. So this is not my theorem, it's a theorem by Gnedin and Pittman. So essentially, all the possible Gibbs-type priors are mixtures with respect to those 3 parameters. So in the Dirichlet multinomial case, you have h as founding parameter. In the Dirichlet process, you have alpha. In the sigma stable Poisson-Kingman process, you have, what is it, gamma. Okay? So if you consider mixture with respect to these 3 parameters, you characterize all the possible Gibbs-type priors. So essentially, this is a Bayesian hierarchical interpretation. So you start with one of those 3 models, you place a prior on those 3 parameters, and that generates all the possible Gibbs-type priors, which is very natural. And if you're lucky, then maybe that actually happens in the Pitt-Maillard. If you start with a complicated formula, you put a sophisticated prior, magically things simplifies, and you get a Pitt-Maillard. Okay, so, but from a practical point of view, essentially we're saying that we have 3 models, and we would like to learn the main parameter, and that main parameter actually turns out to be very important for estimation of biodiversity. Let us see why. So let us get back to the original problem. So estimation of biodiversity. What should we do? So we can start with the richness. So richness is a natural way of quantifying the biodiversity. How many distinct species do I have? So that's the starting point. So the distribution of the richness, a priori, has a known form. It depends on the generalized factorial number, which is this calligraphic n, times the coefficients, divided by the sigma parameter. In the sigma equal to 0 case, you get the limit, and you get the usual formula with Stirling numbers of the first kind. Okay? So what ecologists call the rarefaction is essentially the expected value. Oh, sorry, this is a typo. This should be a y. Okay, so the expectation of this distribution. Okay, so the expectation of that distribution is what is known as rarefaction. Then there is this paper by Antonio Lioy and co-authors in which they found actually the posterior distribution of that. So now I have a sample, how many new species I'm going to get in the future. And so this is not conjugate, but very closely related to the a priori case. You get the non-central generalized factorial coefficient and a ratio of the VNK coefficients. And the posterior expectations are essentially an extrapolation of the rarefaction. So ecologists have this tool called accumulation curves. Accumulation curves are essentially counting how many distinct species I have over the number of individuals. Okay? And so this is a model-based estimate of the accumulation curve in sample. This is a model-based estimate of the extrapolation. So with a plot, I think it's easier. So this is a data set from the Amazonian basin. So in the Amazonian basin, there are about 500,000 individuals that were sampled by many, many researchers over the years. So that's the total number of individual trees. But some of them, of course, are from the same species. And so there are in total, in sample, about 5,000 of them. Okay, so this part of the curve is the so-called rarefaction. Okay, so what we would like to know is what happens if we continue this curve, if we keep sampling. How many new species do we get? And the orange curve is the extrapolation that you get using this formula here, under the special case of the Dirichlet process. And in the Dirichlet process case, actually, the formula is incredibly simple. And for some magical reason, the Dirichlet process in this specific data set works pretty well. And by the way, this is not my idea. It's Hubble that recognizes that. It's the same data set that Hubble used in a science paper, so real science, not just statistics. Okay, so sigma diversity was mentioned before. So we have this plot, but we would like to have a single number of biodiversity rather than an entire curve. So how do we summarize this curve? We could think like crazy stuff, like taking the derivatives, the area under the curve. I don't know, but the unnatural way of summarizing this whole plot is considering indeed what happens at the limit. So if I keep sampling, so if I keep going, keep going, keep going. So there are three cases here. There is case number one, in which we assume that at the limit, we get a finite number. Then there are other two cases in which in both those cases, the number of species diverges. Some people say this is just a mathematical artifact. I'm a more moderate position on that, in the sense that you have a divergent number of distinct species, but only for a divergent number of individuals, which is more delicate than just saying that the total number of species is finite. Anyway, mathematically speaking, the picture is very clear. Mathematically speaking, in Gibbs-type priors, I say, well, in the three models that we have, you start with the richness, you do nothing, you keep going, and you reach H, the founding parameter, which is the richness, okay, the population richness. In the sigma equal to 0 regime, you get the richness, you divide by the logarithm, and you converge to alpha. In the sigma stable case, you don't need to divide by the logarithm, you need to divide by a polynomial term. And by that, you get another constant. So the three parameters of the three building blocks not only are able to generate the class of Gibbs-type priors, actually, they do something more. They characterize the diversity. And so summarizing this, essentially, Cn function describes the three cases. You start with the richness, you standardize that by the suitable function, and you get to a random variable, the sigma diversity, which is deterministic in the three building blocks, but it's a random variable, you guess what, when you put a prior on it, okay? So essentially in the three models, you would like to know what's the biodiversity, you put a prior on the biodiversity, then you learn the posterior of it. And that's how the Bayesian process works, okay? Okay, so this is just a summary, broadly speaking. Sigma diversity can be seen as a rescaled richness. It's deterministic in the building blocks. And in Gibbs-type prior, we are trying to learn it. This theorem here, yes?
So, is H and alpha really constant, or do depend on the sample? Are they random?
Okay, so they are constant only in those three models. Yes, it's a parameter that, I mean, if you use the Dirichlet model, so this is the law of the joint, okay? So, okay. So it's a constant if you assume that H is a hyperparameter, essentially. Once you put a prior on it, it becomes a random variable. Okay? I mean, a proper random variable, a non-degenerate random variable, let's say. Okay, so this is just a simple theorem. This is just a couple of line proof. Essentially, is tying together the previous result, which is due to Pitman, with a posterior distribution. So if instead of starting with the initial value, you start with additional values given the data, you converge to a random variable, which is the posterior distribution of the diversity, which gives another interpretation. So essentially, the extrapolation here, once I condition to the previous data, is converging to the posterior distribution of the biodiversity number. Okay. This is an application, it's very simple. So this is the very same data set of Hubble. There are a lot of data from the Amazonian basin. And then you put a prior on alpha. You can choose whatever you want. But of course, I'm here using the conjugate Stirling gamma because the Alezito developed that with me. And so it's a kind of a natural choice, I guess, because you have a closed form expression for the expected value of the species. You start with that, you get the posterior, and that's the posterior distribution for the fundamental biodiversity number, actually. Okay, and it's nice to see that well, Hubble was not able to provide uncertainty quantification, for sure not in a Bayesian way, but it did several studies on the same data set, and all those values fall within this posterior distribution, which was a nice confirmation that more or less things are working. Well, of course, then you can modify this framework as many times you want. And sorry, before that, there is two nice lines that finally tie together the historical timeline. So I started saying that everything was interconnected with Fisher. Why that? Well, fundamental biodiversity number is nothing but that limit. And under Fisher model, so that was in LaTeX formulas, the Fisher estimator. But this is very much similar, if not strictly identical. There is a proposition for number 75 in Van der Laart and Goshaw book that says that these two things are identical up to one species. Okay, so those are truly the same. Asymptotically, they are the same. And why they are the same? Because this is the maximum likelihood estimator under a marginal likelihood. This is the maximum likelihood estimator under the conditional likelihood. And in fact, once you try them, they literally differ from a decimal value. Okay, in practice, it doesn't really matter. And this is the maximum likelihood of the Dirichlet process. Okay, so you get the number. And then, of course, you can extend in multiple ways. This is absolutely not a fair list. This is strongly biased based on what I know, and also in a way to emphasize people that presented a poster yesterday, like Lorenzo. Anna presented something about how to specify a prior for H based on a model by Gnedin. Polynomial growth. I mean, the Pitman-Yor can be reinterpreted in this way as a specific prior for the diversity. Something that leads nice closed form expression, but that's another way of seeing the Pitman-Yor. Then there is the case of partial exchangeability. So there was yesterday a talk by Beatrice. What about the case where we don't have a single population, we have multiple populations, and we essentially have biodiversities that are related to the groups rather than a single biodiversity number. And then you can incorporate taxonomy. So what about, I mean, in practice, you don't observe a species, you observe a lot more. So essentially, you can say you have the whole Linnaean taxonomy. So things are more complicated. And you can complicate this stuff. Okay, so then we presented those ideas to ecologists. So I was working with ecologists. And they said, okay, you have a number. And then what? And they showed me the actual data. So they said, well, those are the actual data. And in the actual data, we have the main ingredients that we like. So in the actual data, you have N and Y. I hope you can see. But anyway, this is N, the number of individuals, and Y, the number of distinct species that you have in a sample. But then you have a lot of covariates. Okay, so depending on which part of the planet you are. There is the latitude, the longitude, there is the temperature, there is the habitat type, the elevation, whether the trap was made in a certain way or in another. There is an entire pipeline based on DNA, then there is the morphological collection. I mean, there are a lot of things that are recorded on top of the species. And so they have covariate, and those things vary as a function of the covariates. And so yes, this model is elegant, it's nice, but then you have a single number, and then what do you do with that? So the idea was to start with what they do. They do GLMs. And this is a short recap, and maybe not super useful recap of GLMs, but that's what they are. So you have an outcome, yi. You have a set of covariates. You assume that the outcome belongs to the exponential dispersion family of distributions. And then there is the link function, there is the linear predictor, usual stuff. Okay, so this is a slide just to set up the notation a little bit. Okay, so now the question would be, is there an exponential family that is related to a sample-specific diversity? So can we learn that biodiversity by relying on GLMs? I mean, by looking at this data, what the ecologists were doing, we're saying, well, Y is a count, is the number of distinct species. A count, you know, what's the main thing that you do? It counts poisson. Let's try with a poisson. But then you want to control for the number of subjects, okay? So maybe you put that as an offset. You know, you do the stuff called rate model, okay? So you use N as an offset, Y is a Poisson, you just run with that. But, you know, it's maybe not such a bad idea, but what's the relationship, if any, with the biodiversity number? So is there a way to tie those things together? So now the nice bit, and that was a simple proof, but was not obvious at the beginning, is that the distribution of Yn, so the number of distinct species of a Dirichlet process, is an exponential family. And once you look at the formula, it's kind of obvious. I mean, it's already in an exponential, almost in an exponential family form. So alpha, if you take the logarithm of alpha, you get a natural parameter. Then you have the baseline distribution, which is based on the signless Stirling number of the first kind. And then you have the denominator, so the logarithm of what you get at the denominator is the cumulant generative function, okay? So after recognizing that, the next step, the next natural step is to build a GLM out of it, okay? So you assume that all the data points, so the distinct species, are independent rows from a distribution that has this form here. So this is written in an exponential family form. The mean function is the accumulation curve of the Dirichlet process. Okay, so the mean can be written in this way. The variance function can be written in this way. We were not able to show the variance function as a function of mu because it's kind of implicit, but it's there. I mean, implicitly it's there. Anyway, that's kind of nice. I mean, the expected value of this random variable is the accumulation curve that we would like. Also, there is another stochastic representation of this random variable, which is related to Bernoulli random variable. So the binomial distribution is nothing but the sum of independent Bernoulli with the same parameter. This distribution here is the same, but the probabilities are not anymore the same probability. So they are decreasing probability. And those decreasing probabilities are the one of discovering of a new species. Okay, so you essentially are summing Bernoulli random variables with different probability. And that's the distribution that you get. Okay. So then what? It turns out that the Dirichlet process case, so the accumulation curve of the Dirichlet process case is the canonical link. Okay? So the canonical link is indeed the expected number of distinct species that you get out of n sample, which is that sum that you see there. And so you have this nice interpretation in which if you increase by 1 unit a covariate, essentially you're increasing alpha, the diversity, by a certain percentage. Okay, so the canonical link say that the linear predictor is the logarithm of the alpha diversity, the Fisher's alpha diversity. In the saturated model, essentially we are estimating approximately distinct alpha Fishers for each possible sampling site. So that's the interpretation of the saturated model. In the null model, so the one in which you have only the intercept, essentially you are saying that all those data points have the same biodiversity. All the other models are in between, as usual. And there is also this nice asymptotic approximation that tells you that, more or less, ecologists were not doing something crazy. I mean, when the number of observation diverges, so the number of the individual diverges, then the distribution here is actually a Poisson with an offset, okay, in an approximate sense. So the Poisson model, I mean, the number of distinct values is 1 plus a Poisson with an offset, which is also nice. So the regression coefficient that Abel was getting are approximately, I mean, the regression coefficient that we get with this Abel approach are more or less the same of the Poisson case. Then what about non-canonical link? What's the problem with the canonical link? The problem with the canonical link is that it implies a logarithmic growth rate. So what about including other growth rate? Well, we choose a non-canonical link. So instead of getting using the Dirichlet process accumulation curve, you get, for example, this is just an example which is tractable, something like this, something that depends on a sigma parameter, a global sigma parameter. So instead of having a logarithmic growth rate, you can get other shapes. And there is also this theorem. So this non-canonical link is nice because it covers the Dirichlet process as a special case, and it kind of mimics what happens to Gibbs type priors for different choices of sigma. So when sigma is equal to 0, the diversity is exactly exp to the exponential of the linear predictor. When sigma is between 0 and 1, the linear exponential of the linear predictor is just a diversity rescaled by sigma. Otherwise, you have this slightly more convoluted formula, but still says that you can interpret the exponential of the linear predictor are a measure of biodiversity. How do we fit this model? So this is when the talk becomes a bit frequentist, sorry. But you can estimate this model, of course, in a Bayesian way if you like. I mean, it's a likelihood function, it's a CLM. You can use any kind of approach you want. But as a proof of concept, we used the maximum likelihood at the very beginning. So this is the traditional ERLS algorithm. You get the maximum likelihood. It's fairly regular as a problem because it's an exponential family. So not a big deal. And yeah, it's also important to adjust a bit for the fact that, I mean, probably the model that we're using is SME specified. And the reason for that is due to the fact that species in different locations are probably dependent. I mean, the independence assumption is not practically tenable in the sense that if you go on multiple locations that are close to each other, well, some species are going to be in common. That creates dependence. So if you know that there are a lot of species here, it's probably an indication that over there are going to be the same number of species and similar species. So under this assumption, you can still notice though that the likelihood function can be still interpreted as a composite marginal likelihood. So the estimates are still going to be consistent under fairly mild conditions, but you need to adjust the standard errors. And you can do that in multiple ways. One simple possibility, I do not guarantee that this has strong theoretical justification, but this is a classical sandwich estimator. You pretend to estimate the correlation structure of the errors in some way. A simple idea is to simply count the number of the fraction of shared species that you get across samples. And you pretend that it's an estimate for the correlation structure. It's not crazy, but who knows in real data whether this is a realistic assumption. Of course, if this is a good estimate of the correlation structure, then everything works. We tried that, and we implemented that with the usual GLM machinery, and it works as intended. I mean, the habitat low has a higher biodiversity than the baseline. What we have here? Well, basically everything here has a higher biodiversity than the baseline. I don't remember which was, but probably not something very biodiverse. And then we move to the real data set. And we specify the model with something more. Okay, no, sorry. This one was nice because the assumption that the canonical link was actually tenable, was actually a realistic assumption. And also the dispersion parameter taken equal to 1 means that we're not adjusting the standard errors for nothing. Instead here we do that. We adjust the standard errors. We use this more sophisticated model. We get an absolutely meaningful result. So in urban areas, hopefully you can read this, you get a negative sign because it's less biodiverse than the baseline. Okay. And finally, so we showed that to the ecologists, and they said, not so nice, in the sense, well, nice, you get that in urban areas, there is less biodiversity. Thank you. And also we discovered results. Latitude has a major effect. In Greenland, there is no biodiversity. Thank you. So they were not, I mean, they were happy that everything was working as intended, but the scientific outputs were kind of obvious. So that's why Ale is still working on that. So we received the actual data on the globe this summer. So I was not feeling confident to present the whole data set today, but now we have the whole data set. So we actually chatted with them in order to get to actually do some meaningful hypothesis testing. I mean, is there a scientific hypothesis that we actually want to check, rather than just saying that in Greenland the biodiversity is lower? Although there are things that they were already quite excited, like the accumulation curves in places where there were no sampling. So this is probably something that we were never able to do before. In a place, this is Canada. So suppose you want to sample here where there is nothing. What's the expected number of species that you're going to get? Okay. This is already something that they feel it's kind of important and useful. So next steps, well, one paper, so the kind of review paper on the biodiversity, it's on arXiv. The second one is ongoing. So probably the most important thing is to finish the paper as a next step. And then once you have the GLM machinery, well, then all the other, the extensions are limitless, I would say. I mean, there is the Bayesian thing to do. There are random effects. You can incorporate GAMs. I mean, you know, all the infinitely many variants of GLMs are out there to be explored in this situation. And so probably in 20 years, probably we will do something. At the moment, we're trying to make this specific data set to work. And I think with this, I'm done.
Okay, so thanks, Tommy. We do have some time for questions from the audience because we are perfect on the schedule. So please don't be shy.
Maybe just clarification on something that you showed at the end. So you had this picture and you were commenting on the fact that you could predict in areas where you didn't see anything. And thinking about it, I was a bit lost. So I think there is going to be a spatial correlation, right? Are you taking into consideration the spatial correlation into the prediction? Or let's say nothing in Canada there, maybe different than nothing in California?
Okay, so let's say we're taking spatial correlation in the sense that we are using longitude and latitude as covariates. So that's part of the information that we have. So of course, by using that, here we are using splines, but probably we're going to do something more sophisticated eventually. Although to be honest, this already works quite well. So yes, that's using spatial information as a point estimate. As a correct uncertainty quantification, I would say that yes, we're kind of taking care of that by using the sandwich estimator on the regression coefficient, and that reverberates the uncertainty, the spatial uncertainty through this correction. And if you look at the standard errors in the case where you pretend that the model is correctly specified, then the quasi-likelihood version where you estimate the dispersion coefficient, then you finally the case where you specify the sandwich estimator for the spatial correlation. So the standard errors in the spatially corrected case are much wider than the one in which you specify the correct, where you assume that everything is correctly specified. But yes, the spatially is taken into account.
Any more questions? I do have one that relates with with those graphs, with the accumulation curve. So so because we're speaking about animals, so how to interpret say accumulation curve that seems to diverge? I mean, because clearly we don't expect the animals to be truly infinite, but does it mean that maybe there are a lot of species that we have not, say, discovered yet for the first time, so we are very, very far away from being stable? So you have some more intuition on that, besides the mathematical aspect that was very clearly explained in your
Okay,
talk.
so the fact that whether accumulation curve have or not an asymptote is actually a lively discussion in parametrics, but also in the classical community of ecology. So there are people saying, well, there is a fixed limit. Of course, the number of species is finite, and I think everybody agrees with that, but that's not necessarily a contradiction with diverging accumulation curves, because you diverge when the number of individuals diverge as well. And in fact, you can use the Dirichlet process to estimate the number of distinct species in an habitat by simply understanding where is the intersection between, suppose we have this accumulation curve like here. That's precisely what is done in a Hubble paper. So if you go here in this plot, so in Hubble, they do have a rough estimate of the number of individuals in the Amazonian basin. So essentially they say that, well, the Amazonian basin is big like something, and then they estimate the density of trees that you have in the Amazonian basin. And that's a rough estimate, of course, but then you can randomize a little bit to account for the uncertainty of the estimate. And then you simply see, well, suppose the number of individuals is here. What's the number of species that you get in the accumulation curve? Turns out to be 15,000, okay? And that agrees with the other estimates that ecologists have for the number of species. So the fact that you have a divergent accumulation curve doesn't mean that you cannot estimate the total number of species. It simply means that you need to use it in a different way. Second of all, even when it's clear that there is a fixed limit, so sometimes it's useful to use these models as approximations. So especially in genetics, I mean, when the accumulation curve is rapidly growing, okay, so it's almost a line, which is not the case here, but in genetics you can get that. So you have a rapidly growing curve. You can use that polynomial growth rate as an approximation for at least the next bunch of species that you're going to observe in a future sample. And maybe eventually that curve is going to be stabilized, but you're far away from that regime. So it's still a useful model, let's say. Not sure whether this closed the discussion, but at least there are a couple of ideas.
Yep.
So you discuss about actual scientific questions to answer with this tool, no? Can one be like testing if I mean, climate change or human impact is reducing biodiversity?
Mm-hmm.
So you probably need data collected in different time periods.
Yes, and we have that actually. So we do have data collected over different time periods. It's actually a very complicated thing because since those are global data, we had this issue that summer and winter, of course, affect biodiversity in multiple ways. And then the seasons are flipped over the globe. But yes, we do have data over multiple years. And well, biodiversity, I've been told, is something, I mean, it's a gradual process. I mean, sometimes it's sudden, but on the planet, it's a gradual process. But yes, that's absolutely something that you can monitor. So you monitor the alpha diversity, and you imagine to have a gun, for example, where you have time as a covariate, and that the marginal effect of time the exponential of that would be alpha Fisher estimate for the biodiversity over time. So yes, absolutely. That's something that can be done.
That case you have to add maybe the random effects of location specific,
That's,
all the stuff that you were mentioning, right?
I mean, this is an interesting scientific question that is part of point number 3, finish the paper. But